Hello guys, in this video I will talk about the stream function. Consider the simple case of incompressible 2D flow in the xy plane. The continuity equation reduces to dou u by dou x plus dou v by dou y equals to 0. As you can see here, we have two unknowns. So we need at least two equations to solve the problem, but we only have one equation here. What about if we can reduce the two unknowns to only one unknown? That's what Joseph Lagrange, a Franco-Italian mathematician, did. In the year 1781, he introduced the concept of stream function. The function rewrites the continuity equation in terms of one dependent variable instead of two variables. As such, you can solve for the u and v velocity components of the flow field with a single equation. This is how it's done. We define the stream function u equals to dou psi by dou y and v equals to negative dou psi by dou x. To check the validity, first we have the incompressible continuity equation, which is dou u by dou x plus dou v by dou y equals to 0. The equation 1. And the stream functions u equals to dou psi by dou y and v equals to negative dou psi by dou x. Equation 2. We substitute equation 2, the stream functions, into the incompressible continuity equation 1. So we have dou by dou x times dou psi by dou y plus dou by dou y times negative dou psi by dou x equals to 0. We obtain dou square psi by dou x dou y minus dou square psi by dou y dou x equals to 0. The only difference here is the denominators. Is dou x dou y the same as dou y dou x? Well, for any smooth function, the order of differentiation is irrelevant. And since psi is a smooth function in an incompressible flow, so dou square psi by dou x dou y minus dou square psi by dou y dou x indeed equals to 0. With the knowledge of stream functions, you can use it to plot streamlines, which represent the trajectories of particles in a steady flow. Now let's look at some of its applications. We can use the stream function to describe simple flow fields, such as a uniform flow in which the flow velocity is the same from point to point within the uniform flow region. We can also describe other simple flows such as the source and a scene flows. For a source flow, there's a common point. From this point, the flow is directed outwards radially. The scene flow is very similar to the source. There's also a common point, just that the flow is directed inwards. When we put together these simple flows, the process known as superposition, we can obtain a more complicated flow pattern. For example, if we combine a uniform flow and a source, we obtain the streamlines like this. First, this is the common point of the source flow. The flow goes towards the right. At the left side of the source, the flow converges with the uniform flow. The remaining flow coming out of the source will go towards the right due to the effects of the uniform flow. There will be a stagnation point here from which the flow diverges vertically and then it goes downstream. The streamlines of the uniform flow will be divided into those that pass the source from the upper side and those that pass from the lower side. Here we have the dividing streamlines. Notice that the shape formed by these streamlines resembles a circular geometry. It means that if we have an object with a rounded shape like this, the flow around it can be described by those streamlines surrounding the dividing streamlines here. Can you think of any object with a rounded shape like this facing the flow? How about a bullet? Now imagine the year when the stream function was first introduced, which is in the 16th century. Back then, photography hasn't been invented, so you don't have photo to look at the flow. and the use of strict experimental technique to visualize the flow hasn't developed. So the ability to see the flow in this much of details by the use of streamlines is something really incredible. Now let's put together a uniform flow a source and a sink. We have a common point for the source and the sink. The flow coming out of the source and will go to the sink. Something like this. Here the streamline of the source flow will converge with the streamline of the uniform flow and forms a stagnation point from which the flow diverges vertically and then goes downstream. Then the streamline will converge at the right of the sink to form an enclosed region. The rest of the uniform flow streamlines will flow past this enclosed region. So we have the dividing streamlines here, which represent the shape of an object with a rounded front and back. Can you think of any object with a shape similar to this? I'll give you some time. Any idea? How about a torpedo or a simple submarine? Or maybe it just looked like a watermelon to you. After all, watermelon does fly in the air sometimes, and the flow around it might be of importance as a subject of some advanced study. Who knows, right? Along a streamline, we have the streamline equation, negative v dx plus u dy equals to 0. Now we have the stream function. U equals to del psi by del y, and V equals to negative del psi by del x. If we substitute the U and V into the streamline equation, we have del psi by del y times dy plus del psi by del x times dx equals to 0, which is a total change of psi. The reason is the total change in psi is because del psi by del y is the rate of change in the y direction, and that multiplies with dy means the first term here is the change of psi in the y direction, while the del psi by del x is the rate of change in the x direction. So when it multiplies with the dx, means the second term here is the change of psi in the x direction. Therefore, the sum of these two terms is the total change in psi along the streamline, and is equal to 0, which means there's no change in the value of psi along a streamline. So, if we have a family of streamlines for a flow field, each streamline will have a unit value of psi, and that value is constant along the streamline, although this value may change from one streamline to another streamline. Now let's look at some of the physical significance of stream functions. The difference in the value of psi from one streamline to another streamline is equal to the volume flow rate per unit width between the two streamlines. With this equation, you can determine the volume flow rate of the flow between two streamlines. Since by definition, no flow can pass the streamline, so the volume flow rate between any two streamlines will remain constant. And given that the volume flow rate is equal to the cross-sectional area of the flow times the velocity, therefore, as the gap between two streamlines widens, the velocity will drop, and vice versa. With this knowledge, when you look at the streamlines of a certain flow field, you will be able to tell where the flow should have a higher velocity and in which regions the flow velocity should be lower, based on the relative distance between streamlines. The stream function adopts the left side convention. That is, the value of psi increases to the left of the direction of flow in the xy plane. By this definition, can you tell whether the flow is going up or going down? Take a moment to think about it. Well, the answer is going up because sine increases from 5 to 7, and that 7 is on the left if the flow is going up. This is the end of this video. Please try out the exercise related to this video given in the U-Learn. Thank you for watching.